My part was correct after a few minutes. Now we'll see if it's useful. That's the question. I'm going to look at everybody's. I would be sad if nobody seems to be impressed or informed. Okay, 2:35. Let's do it. So today is part 3 of our little segment on manipulation in Clutter. And I have a bit of an agenda today, just because we have a couple things. I want to start by just talking about final projects for a second, since that's starting to be project time. When I was getting good questions at the end of the lecture last time, I was like, geez, if I just made a 3D visualization, this would all be clear. So I made a 3D visualization about last time, and I'll see if that lands a little better. I'll just spend a few minutes of that trying to say what I said at the end last time better today. But most of today is about authoring more complex tasks. Of the this clutter clearing kind of example of doing bin picking that we've talked about, that's the part I haven't given you any tools for yet, and we'll talk through the basic tools that we use and give you a preview. I'm not going to give a full description of PDDL, if you guys know PDDL, the PDDL, the planning language, but I wanted you to understand where it fits in the context, and we'll talk a bit more about state machines and the like. Okay, so final projects. I'm happy to discuss. Some of you have been coming with ideas already. That's great. Some of you have been posting on Piazza or sending emails. That's all great if you reach out with us. But it is time to be thinking seriously about your projects. So a week from Friday will be the first draft of the project proposals. The goal of that, the reason it's a first draft, it's not because the CIM will actually give you feedback on that part of it. But for me, it's a chance for you to tell us what you're thinking and us to give you serious feedback on the scope of the project. Maybe you're saying that the thing you think is going to be easy is actually going to be really hard, is a common thing that I end up saying. Or maybe you could do a little bit more. If you've got multiple people, we want to try to understand if you have a plan for how the different people are going to be able to collaborate. These are things that I've seen enough projects go by that I can give some feedback like that. So the more time you put, or the more thought you get into your first draft, the more feedback you get, right? So please take that as an opportunity, and then we have a future draft, a final sort of proposal, just to kind of lock it in. And oftentimes, if your pre-proposal was great, then you just say, I'm good. We'll be clear about whether you should resubmit the same thing or not. That's a common thing, is that people have worked out what they want to do, and we just say, you're good to go. But if you give you some feedback saying, try to increase the scope, decrease the scope, or did you think about this, then we'll have one more chance to revise that. There are rubrics on the website about how it should relate to your research or not. In general, it's great if it relates to your research, but if it is exactly your research with no changes, then that's not so good. So the goal is, the dream for me is to say, like, I'm working on this thing in research. It's kind of related to the class. If I hadn't taken this class, I would have never tried this new idea that I learned in class, right? And it completely complements your research. It could use the same robot simulation. It should be something about manipulation, please. But think broadly about that. And if you're not doing research in this area, that's fine too, and we should have a lot of project ideas. There's project ideas already on the website. My goal is actually to just take one more pass on that, put a couple new ideas in, and then we'll post on Piazza saying, hey, take a look if you're still looking. There's nothing wrong with the list up there. I just haven't put last few ideas that we could put up there for this term, and I'll do that tonight or tomorrow. Any questions about the project? There's links. Oh yeah, please. You can do either an individual or a team. You can do teams across undergrad and grad. That was a good question we got. Just as you understand the logistics, they have different requirements at different times. So, but we're fine with that. We're happy to deal with that. And you can do You can do more with a team, of course, but you should have some sort of a plan for how the multiple people will interact.
What size of teams?
No bigger than 3 is what we've been saying. Yeah, 2 is very common. 3 is fine if you can have a good plan. Any other questions? I love the projects. It's the best, right? So it's partly because you get to go with some idea a lot deeper than we can possibly give you in lecture or in a problem set, but also because you guys come up with such good stuff, and it's like the most rewarding for me. And I learn a bunch from you guys, from seeing what worked, what didn't work, what you tried. Maybe you tried to implement a paper, and I get to learn about the paper by your implementations. So I really, really enjoy it, and I hope you do too. Yes? Absolutely. Yeah, so there's actually a list on the project page on the website. I almost want to put it in big bold, but there's a list, like the last bullet says, here are some projects from previous terms, and I have a list of some of the, I mean, they're, the ones I put up are the ones that people gave me permission to put up, and there were some of the ones that were the most successful in some ways, so they're not like every project that has come out that was an A, is on that list. But it gives you a sense of some of the things that people did were really amazing. So take a look at that. If you still have questions, I'm happy to try to give more examples. Okay, so last time I was drawing force diagrams. I was like trying to use my thumb coming out of the blackboard, and I really wanted to have a little bit better picture for you. So I went and made that over. This is what I did with the long weekend. You also see the state machines I came up with too. But let me try again just to say the friction cone, force cone, contact wrench story with a little bit better pictures. Okay? So we talked about this, the forces. I'm going to just do it on slides because it's mostly what I wrote on the board last time, and it'll go faster if I don't write everything again. But we talked a lot about forces, and in general, the spatial force, the generalization, is both a torque plus a force, right? So we said, torque plus a force. This is applied at some point in space. You can name it. It can have an expressed in frame. Okay. You can add them. There's the spatial algebra of spatial forces, right? Which sort of fits in. But the most important one that came up was that there's this, if you are considering a force applied on a body, I'll draw just the simple version of this to foreshadow my animation here, right? If I have a force being applied directly at a body, it's kind of weird. If you might think it's weird to think about, how can I apply a torque, right? That's not why the torques appear. Maybe at every point that there's a force being applied, it might be just a 3D force with no torque immediately. But I can summarize the result of this force at any point on the body. And if I want to think about its effect as if there was something applied at this point on the body, then I can write this as a force plus a torque. Okay? And if I want to think about the net effect of multiple forces applied at multiple bodies, I can move them to the same point of reference, sum them up. Okay? So the way that you move between thinking about a particular force being applied at a particular point on the body to a different point on the body, the torques come from the cross product, which is something you know from physics, from intro physics kind of stuff, right? So the cross product of this vector with the force gives me the torque. Okay, and then we talked about, please ask any questions if you have them. I know I said that last time. And then we drew these diagrams and we talked about the friction cone. And I got a couple of good questions after, just like, what is going on with the cone? Like, why is it not just one force? Why can't the world decide and pick one force, right? And the world will, of course, decide and pick one force. But the laws of friction that we describe are saying that friction will do whatever it needs to resist motion, but it'll pick one element from this set, which is a range of possible forces. They all live in that cone. Right? That's the way to think about this friction cone. The rules of friction say, I will pick whatever force inside that cone that will keep me from moving at all relative to the point that it's being applied. And if it is moving, if it's just unable to completely stop motion, it will dissipate energy as much as possible. So as an abstraction, to think about the things that friction could do to me, it's useful to think about a whole cone of possible forces. And if I say there exists a force inside the cone, then I know friction has the ability to stop my motion. Right? So it's a little bit weird to say, I'm not picking a force right up off the bat. I'm going to think about all the things that friction could possibly do in order to resist motion. And that's what the friction cone is. Okay? Get into my animation here, okay? So yeah, I guess I answered the check yourself. That's a flub. The interesting question then is, if you think about the set of possible things that friction could do to you to resist your motion, and you think about the basic algebra of moving forces, applying cross products, the algebra, given that the points of contact are all fixed, is all linear operators. These equations, if P is known, you're not moving the point of contact, then the way that forces change through these equations is always linear. And if you if you replace a particular force with a whole cone, and you ask how a matrix changes the cone, it turns out it stays a cone. And that's the magic of what I was trying to talk about last time, but I didn't have the animation to help me. Okay? I didn't write this on the board last time, but I'm putting it into the notes more carefully. The point is that you can think about shifting, so the friction cone, right at the point of application, you might say there's no torsion. There's no torque at the point of application, and the cone at the point of application is defined by the XY components in my contact frame being less than the coefficient of friction times my Z component. That's what defined my cone. That's just the friction cone definition. If I want to shift that whole cone, right? If I want to shift this whole cone of possibilities to here, then I can apply my same linear operators of just shifting the force and then getting a cross product to that whole cone. And that's what I'm going to animate now. Okay, so okay, here's my little animation, all right? So I've got a box. I'm not even gravity. It's just a box stuck to the world, okay? And I'm applying a point on this box. The green is the immediate friction cone, and the red is the friction cone if I thought of it from the point of, as if the point of application was the center of the body. Is that clear? Now here's the weird thing, is right, the friction cone has 6 elements. So how do I animate a cone in 6 degrees of freedom? I'm going to just cheat a little bit, right? And there's a place where it's already going to be misleading. I'm going to draw this cone, the 3 XYZ cone. I'm also going to draw the torque cone as if it was independent, but it's not actually independent. So it's like the projection of the 6-dimensional cone into 2 cones. I think that'll be clear in my picture, but that's what's happening, is I'm going to draw 2 cones to represent the 6-dimensional space. Okay, and then I can move the body around, and what you see here is that no matter where I apply the forces on this body, I still get the same XYZ component of that force at the body. That doesn't change. What changes is the torsional component. As I move, depending on where I move around the body, I get a different torque, a different wrench that's representing my cone. And it's a funny shape, right? It's low dimensional. You have to look at it from here to see what's happening. Why is it low dimensional? Well, we know every element in that set has to be orthogonal to the cross product. It has to be orthogonal to the line from here to here. You can't produce torque except for orthogonal to that line. And as I move further away, right, I'll get this elongated cone. I'm drawing a truncated cone. The real cone, if there's no limits, would go on forever, but in those directions. Does that picture help at all? Oh, man. Does that picture help at all, right? So why is it torque over here now? Is that if I am applying a force that goes here, then my friction cone should be in, I got the right direction? I better get the right direction. I can only resist motion in one axis, right? So I resist motion like that. Yes?
So blue is where the torque can exist. Is that true?
That's correct. So if I were to come up to this body and apply a perturbation, and you ask what can that frictional force resist, if the perturbation torque I applied is inside that cone, then friction can stop me. So if I apply a torque that's pushing me into the finger, it can stop me. But there's a whole other direction. If I applied a torque in the other direction, where I'm just going to move away from the finger won't stop me. That's why it's one-sided, right? The point I wanted to make last time was that the antipodal grasping is a good strategy. I think with this picture I can land that idea. I'm not as confident now as I was a few minutes ago, but let's try. I need a second finger. Okay, 2 fingers now, okay? I can move them around. Okay, if they're down here, what happens is that the friction, the torsional effect that friction can have, they're both in the same direction, right? That's not going to, there's a whole motion that I can't resist whatsoever. But if I move it up and I'm more antipodal, then something beautiful happens. So not only are they going in opposite directions, that's good, but because they're coming from a different cross product, they span a different space, right? So this one can accommodate wrenches that are in that plane, and this one can accommodate wrenches that are in that plane. It makes a nice little butterfly kind of looking thing. The rules of now saying, can I find something that resists me in either of those forces, are using what's called the Minkowski sum. If you try to ask, if I apply a new wrench, can the sum of the 2 wrenches resist my motion? Then that's equivalent to asking if the wrench is in the Minkowski sum of those 2. And now that these are spanning the space, I have a nice strong wrench that I can resist with. Okay? So, maybe you're totally on board now, and that would be awesome. But at very least, when things line up, they look pretty, right? I mean, they look like they're covering a lot of space, right? And it's an effective grasp. And it's different if I move them off to the side, but the story is still sort of the same, right? So as a general strategy, if all things created equal, I'd like to be nicely aligned around the center of mass, because then there's no gravitational torque to resist whatsoever, and I only have to worry about external forces. But if I don't know much about the object, what we did last time was we said, let's just go ahead and just pick antipodal grasps, because without knowing more, that's a pretty good strategy. Yeah?
So because of the Minkowski sum thing, that's like the one blue thing dragged across the other blue thing?
Exactly.
Does that create does that fill the whole like 3D space all around it so it can resist everything?
That's what I want. That's the picture I want. The details are just a little bit more subtle. So the question was, let me repeat for the, so the Minkowski sum, you should think about as taking one element from the first set and then applying the entire second set to every element of the first set. So it's like you can drag it around. So take this cone here and apply it to every possible force in there. And so yes, it looks from this picture like you can create the whole space. The only thing that's a little bit misleading is because I've done the projection of the six-dimensional space onto the 3D, you don't get to independently pick X, Y, Z and torque. So you have to be a little bit more careful about saying that. But to first order, absolutely the picture I want you to have is that the Minkowski sum of that resists all torques. Yeah? Pure torques, I can say with confidence right from this picture, you can resist pure torques, all pure torques. Yes?
So that's even a torque if it was like the 2 points are like this and then it was this way.
Right? So and think about how that would happen, right? So because the reason that you can produce arbitrarily large, it's a function of your normal force. It means you'd have to squeeze harder. But if you're willing to squeeze harder, then you can, then under this friction law, you can resist all of those torques. Yes?
Sorry, could we see the case again with a not antipodal?
Yeah. I think the difference about spanning space is not, I think it becomes, the coupling becomes more important, right? I think the optimality of antipodal grasps maybe isn't completely visible in this projection, if you think about only spanning the spaces. But maybe the magnitude already tells you something that it could be good. Okay. It's a little better maybe, but that's this wrench visualization. You can play with it. I mean, I pushed it to the deep note. So you can play with that and tell me if it makes sense or doesn't make sense. I want to hear if it was worth it. There was a weird, I spent like way too much time making this animation because there was a bug or not a bug, but a known limitation in the way the WebGL works in the browser. I was sure that my math was wrong for hours, and then it was not my fault directly. Anyways. So you better have learned something from that. Okay, and the Minkowski sum is sort of the beautiful part of that. Okay. So let me tell you now about, back to the clutter clearing. So we were talking about this project, with the robot moving things back and forth. That's kind of our short-term goal, is you should be able to program a robot to do stuff like this with no knowledge of the objects, with dense clutter, right? And to do its thing. So that's the other thing I did. Hopefully it'll load in a reasonable amount of time here, is I finished that example. Remember how I showed you my halfway example and it ran directly into the camera and it dropped the thing and you guys all laughed. You made a big file, so let me. I can run it locally too. Okay, I'll run it locally instead. It's taking a long time to load. I made a big file, partly because I replaced the the red bricks with the other YCB objects. I thought that would be a little bit more interesting, but those stupid meshes are so big, or the texture maps are so big that it takes a long time for it to come in the browser when I'm in campus Wi-Fi. Okay, here goes. Random YCB objects thrown in a bin. Now it's going to start, it's going to do our whole pipeline, right? So there's cameras here. They are going to do the point cloud processing. It waited for a second for the initial conditions to fall. It's going to then take the point clouds, do some point cloud processing, find the normals, take random samples, do the antipodal grasp, the grasp selection. It tries 100 random grasps. It picks the best one by our little grasp metric, right? And then it does everything we've talked about so far. It makes a simple plan of the gripper frames. It interpolates that into a piecewise pose trajectory. It then runs differential IK. This is the whole tool chain, okay? And it's going to do its thing. It's going to pick up and slowly move all the objects. It will still fail every once in a while, but it's pretty good. And actually, the failures are to the point now where I think they're pedagogically interesting, right? It's not like I didn't spend enough time with the code. It's like we haven't done motion planning yet, and so we need a better tool for this. And this will go all day long. Every time you run it, it'll have different initial conditions. It also has some fairly, not sophisticated, but it's a basic, that's awesome. Some basic recovery maneuvers. So sometimes it'll pick, remember the antipodal grasps are just a heuristic. Sometimes it'll pick right on the edge of a soup can or something like this. And see, that was a kind of a double pick that it started to do right there. It rotated, it didn't drop this one. But if it does fail to grasp, it'll lift up, it'll realize it failed to grasp, it'll go back down, right? It also, when it can't find a grasp, I'm going to write all of this down. When it can't find the grasp in the first bin, it'll transition to the second bin and start picking from the other bin out. Oh, see, look, it stopped. Whoop, and it realized that it did that, and it's going back to pick a different thing. Right? That extra level of robustness makes this something that but it knew it. See, it realized it, I think. Yeah, come on. And try it again. See, that was one where I was like, that failed, but that's a lesson, right? And it'll keep going to the point where I just let it run at night, and I came back, and the funny thing was all the little things you do to make it robust. So for instance, I actually put an invisible floor underneath there. Why? Because it every once in a while does drop objects, just like the real robot did. And if they fall to negative infinity, then it makes my contact solver fail, because that's numerically bad to have a negative infinity and like a number around 0, right? So now there's a floor, and they can only fall to like 1 meter, okay? And then because there's soup cans, I had to put like lips on the floor, because they would fall to the floor and they would roll off the side and then fall to negative infinity, right? So all the little things got figured out, okay? And now it just will run all night, and with some probability, depending on how long you sleep, it'll come back and many of the things will be on the floor. But it didn't crash, and it kept going and does its thing. The other interesting one that maybe I kind of hope we see, but I have mixed feelings about, is that it differential IK can get itself in a bad state. Yeah, that's you see, it didn't try to grasp there, but the hand is unable to get where it's trying to grasp, because the differential IK is commanding a certain thing, it's getting a certain different thing. But look, it's going to try, I think, 5 times, and then it'll give up and say, I'm done with this bin, I'm going to go do the other bin. That was even worse. Is that 5? Maybe this is 5. See? All right? That's like intelligence right there. Okay, yeah, and so there is one other super interesting thing it does, which is that sometimes diff-IK will actually, because it's not thinking about the joint constraints of the robot, it could choose a trajectory that goes very close to the base, and then the arm starts kind of getting a little funky, and the Jacobian, it'll get itself kind of tangled up with just a diff IK view of the world, because it hasn't thought of anything about the joint constraints of the robot. It's just thinking about moving a hand through the world, and that's an impoverished view of what the robot has to do. So there's the last thing I had to do to make it sort of nice and robust is that if it got itself all tangled up, if the tracking error of the hand compared to the commanded hand got large, then it would say, okay, I give up, and it would switch. It would turn off differential IK, turn on just joint control mode, and just go, I'm going to come back to my comfortable home position, and I'll start again. Things got bad, I've got a safe space, and I'll come back in again. Yes?
So in, I feel most manipulation papers and things like that, when you have a video showing demo results, there will tend to be the 10 times speed thing. So what kind of step in the whole process is the most sort of time consuming?
This is all running at real time right now on my computer, on this laptop. Yeah, so that's 1x right now.
When you're putting this on a real robot, would it be running at speed?
The only thing that would be different on the real robot would be that physics would definitely run at real speed. So yeah, this is just running at real time speed. Yeah, I mean, the limitations of the motion planning are partly because it's simple. I could spend more time making motion plans, and then you might see the famous robot pauses where it stops to think about a motion plan and then moves, which the community is getting better at, and we should aspire to not have. But there's no pause. There's the one little thing that cheats here is that the simulation clock can stop while I think in this version of the simulation. So, but you would see that if it looks like it's frozen, and even the physics is frozen. That's because it was thinking for a long time. But I don't think there's any computation that's really sub. And I'm simulating at a pretty conservative simulation DT just because I wanted to not have anything. It can crash. I will list down the failure modes in a little bit. It can crash, but I've only seen it crash at the initial conditions. If my random initial bin thing put things in deep penetration, it could potentially blow up.
So on a real robot, what is on actual hardware, what is the bottleneck for the speed? Is it the motion planning in this case? What's stopping this from running faster?
I could make the robot. I could make the trajectories faster. I chose relatively slow trajectories. If I did that, then I think yes, that's a great question. So there will be joint limits on the robot, joint velocity limits on the robot that would prevent a lot of times our factory robots, this is originally a factory robot, are geared to move fairly quickly, but not super fast. They're not supposed to be throwing things across the room and stuff like that. And some robots are, right? So there will be joint velocities that will be a constraint at some point. On EWA in particular, you can hit the joint velocity limits. If I just used this differential IK controller, then I would also worry as I started getting close to those limits that my tracking error might increase. And so my pick success or my running into things would increase. And a better controller at the lower level or tighter gains, if everything's stable, could make that run faster. I hope to show you some beautiful motions of the EWAs and hardware soon, on real, before we get too far in the class. Yes.
Can you maybe repeat which object does it take first, and which is that random, or does it kind of decide?
You know the algorithm. So it looks at the point cloud. It doesn't know anything about the objects. It looks at the point cloud. It finds normal antipodal grasps. It takes my scoring function and takes the best antipodal grasp score. So it could do anything. There's actually a pretty funny failure case. If it drops the object immediately down in the bin, then it backs off, but not enough. I could easily have fixed this, but I just didn't. It backs off, but not enough, and then the hand is still in the camera, and it sees a point cloud and some really appealing antipodal grasps, so it starts going, in thin air trying to pick itself, But then after that, it gets out of the way, and so it's just a one-time snafu, and I let it go. Okay, so I feel like you know how to do that. Oh, sorry, go ahead.
What's stopping it from finding an antipodal grasp on the edge of the bin and trying to put it off?
I crop. So I feel like it's not cheating, since I know where the bins are in this application, to just crop the point cloud to be in the interior of the bin. So it won't find that. Although, one strategy for getting that one, I guess that one's just going to hit me every single time in this run, right? Because it's never going to move, and every time it's going to be the last one it tries to pick. So every time it's finished with the X bin, it's going to try to do this for 5 or 6 times. On the real robot, we did something where we kind of pushed it out of the corner. That was a pretty good way. But the other thing we did, actually, to your point, was it was really good to pick the bin and shake it. That was another good way to get things out of the corner. But I didn't let it do that. So you have the entire toolkit for this, except for the high-level recovery type planning. And so I want to talk about that now. Lesson learned, I won't put an enormous file in the middle of my presentation. Okay, just going to leave it there even though I'm not quite ready for that, just so that the browser is responsive. Okay, so the way that I programmed that was with a state machine. So I chalk over here. Which is the simplest type of programming at the sort of task level. Where did I put the, oh, here it is. Must be getting old. Okay, so I want to talk a bit about programming sort of at the task level. That's what people often call it. Right? Not the individual motion. This is maybe as opposed to motion planning. Task planning is a high level of what should I do in what order to accomplish my long-term goals, right? Should I be picking out of the bin on the x-axis or the bin on the y-axis, for instance? You know, did I drop something? Do I have to stop and take a recovery? These are the high-level plans, okay? And the simplest approach we'll talk about would just be writing a finite state machine. Which if you've taken an algorithms class, you've seen these. It's called them FSMs, for instance. There's their theory of computation class, thinks about state machines and what they can describe and the like, okay? So this robot, or this demo, has 4 states. It would be better if it had more, probably, but I implemented 4 and got pretty far with that. So the first one is just waiting for objects to settle. My warm-up phase, because remember I initialize the objects in the sky and they fall down, and until I put this mode in, it would try to pick, it would take the point cloud when the things were still falling, and then it would be trying to pick the objects at the sky, but they had, you know, by the time it gets there, they were long gone. So that was ridiculous, and I decided to add an initial setup phase where it just waits for a second or 2. And then I'm going to be picked from, I'm in a mode where I'm picking from the X bin, which is just what I'm calling the bin that's on the positive x-axis, because I didn't have a left or right, obviously. A different mode for picking from the Y bin, which is actually on the negative y-axis. And then I have this go home mode, which is when things get bad, it shakes itself out of shakes itself out of problems and does the right thing most of the time. So I can think about the way that those modes interact by drawing a simple state machine diagram. I guess there's also technically one more, which would be done. I didn't call it a state because I just used an assert statement. If it can't find any objects, if it tries like 6 times and there's no place to pick in 6 times, then it's like I'm just going to assert failure. Okay, but I've got my weight, I've got my pick from X, my pick from Y, and then my go home. And it's useful to think about organizing the behaviors of the robot in a graph type structure, where I can think about, from waiting, after I've done waiting for the objects to fall, I allow it to transition to either of these two possible states. It prefers to go to pick X. I'll tell you the conditions in a second. Certainly, if I'm picking X and I've decided there's nothing left to pick, then I can transition to picking Y. If I'm picking from the Y bin and I can't find any grasps, I'll switch back to picking from X. Okay? And my logic is basically deciding, what would I do to continue here, and do I need to transition to the other mode? Right? Similarly, from either of those states, if I get myself with large tracking error, then I can just give up and go home. We didn't see it happen once in that. It hopefully doesn't happen too often. And I can do that from either of these states. And the go home technically it almost always goes to pick X, but it could actually go to pick Y if there was nothing in X. Maybe I'll even say it really kind of goes to pick X and then transitions from there here. That's how I coded it. Okay, so this this edge here, if I were to just draw it, like what are the conditions on this? The condition on this is, am I done waiting? Like more than 1 second has elapsed. And I found a grasp in the X bin. Okay, this is simple stuff, right? But that's the logic I encoded on that edge, effectively. Okay, and similarly, I'll transition from here to here. If I can't find any more grasps here, and I find a grasp over in Y, then I'll switch mode, picking in Y, right? That way we'll repeatedly pick from Y until it's roughly done. So it's staying in this state, right? And then it'll go back. If I had no internal mode logic, then it might pick from X, and then just the next time it might find X again, and it'd be kind of annoying. It would just move one object back and forth, right? I want some sort of persistence saying to pick from X until you're done, then pick from Y until you're done. So I make these edges not transition until you've failed to find a grasp, right? No grasp. Okay. Now it turns out to be a powerful methodology, right? I can transition to this if I can't find any grasps, right? That's the no grasp cases. This is a very simple version of the basic state machine machinery, but you'd be surprised how many robots you've seen out there that are probably using something very much like this, right, to program the task level. The reason you have to think about it like this, so we're used to writing procedural code. You're used to writing code that says, do this, then do this, then do this, for loop, while loop. That's the way we're all most used to writing code, okay? You don't get to do that if you have to be a robot or in a simulation where you have to have an answer, you have to have an action, something that you must output at every time step, right? I can't be like somewhere in the while loop, doing my thing. You must have an answer at every time. And that's what changes the programming paradigm from instead of the pure procedural logic to something that's organized more like a state machine, or more like some behavior trees, or more something like this. It's the requirement that you must tell me what to do at every time step. You are not allowed to go off and think forever. All right, so how do you implement that as a system, right? Because we're trying to use this, we're going to ultimately write our planner system. Well, it's not that hard to do. I'm actually, I'm very interested, maybe at the end of the lecture I'll ask you again about what you think would help you the most in your projects. And maybe you could even tell me on your project proposals, because I've always felt like low-level control, motion planning, even low perception, we've given you a lot of tools for that, but people don't feel limited in their projects by this level, because I haven't given you lots of tools for this. So you could tell me what is most useful. But the simplest version, these kind of state machine diagrams are very easy to write in the systems framework. All you do is use the simplest version of it. There are more advanced versions that actually do event detection to decide to transition. Let's leave that out for now. Let's just say every DT, every time step, I'm going to start up, I'm going to wake up, I'm in one of these modes, and I take whatever action that's inside there, and I output that to my output port, and I'll decide, should I transition to the next one for the next time step? That's a simple, discrete time difference type equation type system. It happens to have complicated logic, potentially, the conditions about whether you change. It's not a linear dynamical system, but it's a perfectly reasonable conditional difference equation, okay? And you can do that by just saying, I'm going to go ahead and tell myself to update. In that example, I updated every 0.1 seconds. The simulator is taking time steps at like a millisecond, right? So the physics is updating very often. The planner is only updating 10 times a second, right? Because why would you don't need to decide things if I drop the thing at 100 or even 1,000 hertz, right? Okay, and then so basically it says, call my update function every 0.1 seconds. Okay, and then I'm going to declare that I have some state. I tried to use words, and I used a Python enum to use just to make it readable. So if I want to use a Python enum as my state, that's what we call that an abstract value state. I can tell you if you like why it's abstract value. Maybe you care. It's a programming paradigm called type erasure. Okay, so basically I want to be able to pass things through the systems framework without understanding its type. Think about converting it to like a void pointer, void star pointer, or something like that. And I could take if I take any kind of type and I want to turn it into something that I reason about in the systems framework, I can make it an abstract value. It erases the type, it passes it through, but the people who read it know how to put the type back on. That's what the abstract value make and abstract value get does, is it just it erases the type and passes it through and then adds the type back. So if it looks weird in the code, it's doing something clever, standard? I don't know. Okay. So I just say I've got a state here, which is of this planner state type, and its initial value is wait for objects to settle. Right? Simple. And then in my update, I can get out of my context, so that just declares something that lives in the context, which has a erased type. I don't even know what it is, but the context can reason about it with the type erasure idea. And I can get it back at the beginning of my update from my context, and then I can write it to my context at the end, whatever my new decision of my new mode was. And in the middle, I can do all kinds of logic about which state I should go to next, what my actions are during that state. That's the basic way that you write a difference equation that's using some sort of abstract type like a mode that I'm in. Do people like when I talk about that, or like this isn't real robotics? Yeah? Okay. Okay, good. Okay. And then the other piece that's happening here to make that work is when I transition from wait to pick, for instance, when I transition into either pick X, pick Y, or even go home, I'm actually calling my planner. Only on the transition, not when I'm inside it. I call my planner saying, when I transition in, I'm going to decide from where I am right now, how do I go down and pick and place? It's using exactly the stuff you've known. I pulled it right out of the previous notebook. It uses make gripper frames, make gripper pose trajectory, make gripper commanded trajectory. Right out of the existing examples, okay? But I want to save that plan so I don't have to recompute it, so I add that to my context too. Right? I just say I'm going to take the whole plan, which is a piecewise pose or piecewise polynomial, and I'll register that with the context also. That way it's available when I'm inside here. I can pull up what's my plan, and I can just evaluate the trajectory at the current time. That's the architecture. So you can imagine assembling pretty, I just write if statements, in order to make this state machine logic, right? And I can make my plans and declare any internal state that these things need with the systems framework. And it can do all these things. So the architecture then is I actually pulled out just to, whenever you can be more modular in the code, it's that way I can reuse this in the next example or whatever. I tried to pull things out. So I have the grasp selection algorithm is put out into one system. It expects 3 cameras to tell me what the point cloud are, but I use 2 copies of this. I use one for the Y bin and one for the X bin. I just tell them for the one bin, you're going to use cameras 0, 1, 2. The other one, you're going to use cameras 3, 4, 5. Okay. Body poses is one of the output of the manipulation station, which just tells me where my gripper is. That's what roughly it's the internal state estimate of the manipulation station. And it outputs my, it does the sampling algorithm, and it tells me what the cost was and the best pose, the best cost and the best pose. If that cost is infinite, then I've considered myself to have failed to plan. Okay. Now the cool thing is, the systems framework tries to optimize some of these operations for you. So if nobody asks for the output of the grasp selector, then it doesn't do any computation. It only does that computation on when you say, give me your output. So the algorithm here just says, sample 100 points, whatever, but it's not running most of the time. It's only running when I transition in the planner on this, or I decide to transition, and I ask, what's your grasp? So there's just a mental switch of saying, how do you write code that gives an answer every time? And state machines are a way to think about that. But otherwise, it's pretty standard stuff. The planner, it has a bigger job just because, so that this X bin grasp and Y bin grasp are coming from the 2 grasp selectors. But it has to know where the arm is and where what's the current gripper open and closed. Basically, this is the gripper pose and this is the gripper open close. And then it makes its plan. It looks at what time it is, it looks at the plan that it's already saved, and it just pulls out XWG, right, the gripper commanded pose, hands that down to differential IK. All the other 3 are just to make it so you can stop using diffik and go home if you need to. I have to be able to switch between using diffik or not using diffik downstream. That's what my control mode is. I have to send the EWA position trajectory when I'm doing that. And I also have to tell diffik to stop trying to integrate and just look at the current state of the robot. Otherwise, if you turned off diffik for a while and then turned it back on, it would have no idea where you are and it would command something completely wrong. So you just have to be able to say, hey, diffik, look at your current state. Don't try to integrate forward. Okay, so I would say those are just details. I was borderline about whether I should even put them in, but I think it just adds so much more robustness and it exercises the ideas a little bit more. So as an example, I thought that was useful to have. Yes?
Once the gripper takes the object from its bin X
Yep.
and goes to bin Y, how does it decide how far down it has to go?
Yes.
For these
Yes, as you were asking your question, I was anticipating your question, I realized I forgot the self-transitions. But you asked something different, so I will ignore that arrow. That is completely hard-coded. Well, just to make the demo interesting, I pick a random point in the bin to put it down. It goes to a stereotype gripper. This is the make gripper trajectory. I just have keyframes, right? And every time I'm going to put something down, I pick a random place somewhere in the box, and I pick that, and then I do the pre-pick, post-pick stuff to set it down. And every once in a while, you'll see something ridiculous, like it'll stack mustard bottles, right? Because it just randomly picked the same place a couple times in a row, and that wasn't a good idea. But next time, probably if that's a tall mustard bottle tower, it'll tend to knock it over next time, and randomness has been restored. Entropy is restored. Good. So I just want that to be, I want you to feel like you can do that, right? And you have to look at the example maybe or you can just pull this example up and adapt it, right? I want that to be available for you. But it's really, you can author pretty complicated things pretty quickly. And people do, right? So, well, let me just, I guess I'll say my failure modes first here. I kind of made a list as I was watching it, like what actually makes it fail, right? And I could burn down any one of these and make it never happen, but I thought it's interesting at this stage of the class and say, what's actually failing. The first one is my initial conditions, like I said, is kind of a silly, and with some probability, like the mustard bottle could be inside the soup can, and multi-body plant says I can't find forces that will get me out of collision in one step, and it fails on time 0, basically, right? So if it does that, forgive me, just start it again. It's all good. Again, that I could make a better initial guess sequence to resolve that. Motion planning becomes a real bottleneck. This simple heuristic of grasps is too simple, and it will occasionally bump into things. It will occasionally collide the object it's picked up with the bins. It'll occasionally go too close to its own base, so that like if it chose to go from that corner to that corner and I just made a straight line interpolation, it'll go way close to its own base, and the arm starts like, I don't know what to do about that, right? We haven't respected the joint limits of the robot, and so differential IK becomes problematic for those kind of reasons. Ergo, we will spend a week on motion planning in a few weeks, and we'll make that way better. Perception we talked about before, even at the antipodal, but you see it in this demo regularly, right? It'll pick at the corner of an object, and then the object will be swinging around, right? Why? Because the wrench generated by the gravitational force is outside the current grasp's friction cone. And so it'll swing, right? It does do double picks like we talked about because it doesn't know what an object is, right? And the phantoms, like I said, it tries to pick itself. If the hand was in the point cloud, it'll be like, oh, that's a good place to pick, and it goes up and just picks the phantom hand. That one would be really easy to fix, but I just thought it was hilarious, so I left it. And then the other ones are actually super interesting, I would say. Like, it's actually very hard to do much better in this case. We will do it. We'll try to do it. But we'll use force control and non-prehensile manipulation is what it's called, to do things that it's not just picking in place. We'll have to like use the side of our hand to push objects into the corner, apply forces to get it to lift up so we can get our hand under it, right? It's not just about getting your hand around it and squeezing. It's going to be much more than that. And when objects get stuck in the corner, or I actually had to remove the Cheez-It box from my list. Cheez-It boxes are not allowed in this demo because they constantly would like block all the other objects with something that was too big for the gripper to pick up from the top. And I was just like, no Cheez-It boxes, that's it. That's for next week. Okay, so if I were to just, I wanted to even, because we got to a certain level of robustness, this is like the weakest robustness I would ever talk about being robust, but it's actually interesting to think about, like, what would I do if I were to start now applying our stronger tools to make that more robust? There's actually very strong tools that you could apply, and if you've had an internship at an autonomous driving startup or something like this, right? You might have used some of these tools, right? The difference of going from a little toy project to something that has to work every time, which is far from right now, but there's great tools that we could use, and they're all available if you choose to use them for your projects or whatever. But for instance, when we were working on this was also very complicated at the task level, right? And one of the things that happens is when you're doing so many different things and you have task level interacting with low level controllers and all these things, really bizarre things can go wrong, right? When you're writing code, you should try to write, almost always, you should try to write unit tests or component level tests. That's the only real way to write code, is to every time you write a small function, make sure that function does what you want. But for weird interactions between the components that happen when you start taking all this complexity in, you have to do more. You have to do some level of system integration testing. And we're already getting to this point with this simple clutter clearing demo, right? So the way that we do this, and again, this is part of the motivation behind the systems framework, declare your state, declare your randomness, is we have a Monte Carlo test suite, right? You can run off in the cloud lots of clutter clearing simulations. They're all deterministic, given the initial conditions of the of the initial context, which includes the random seed that governs everything afterwards. Okay? And you just let it go off into the cloud and run, and you write a little thing that detects whether it's a good, a success or a failure. And it tells you in the next morning how often you've failed. It'll even make a little movie and put it in your inbox if you want, right? And say like this, it'll record the last few seconds and tell you, these are the statistics of failure and these are the specific failure cases. Okay, and that's how you just hammer on that. You hammer on that, and you actually make your Monte Carlo tests harder if I make the initial conditions more diverse or if I add more sensor noise, right? On that project, it was actually very interesting because we had like the red team that was trying to make the noise models more aggressive and other things like this. They were trying to make the simulation harder to pass. And then we had the people that were trying to make the robot better. And so there'd be a night where someone would, you'd see like git commit, 1492 or something like this, and then and they would suddenly the score would go way down because it would start failing more, and you realize, oh, they added new noise models to the dish rack detector, right? And then you see like 3 commits later, someone fixed it, and then it goes back up. And my dream was that we'd like go up and like hit 99.999%. That's not what happened. We stayed basically flat because the red team was just as fast as the good guys, right? But that was good because on the real robot, on the real hardware, we got to 99.9%. But we made the simulation like so aggressively bad. It'd be like an autonomous driving, always trying to drive down through, I don't know, downtown New Delhi or something like that, or like a bumper cars or something like that. It was the simulation was throwing everything at you all the time, and the real robot was way easier by the end. And so you can use the Monte Carlo simulation suite if you like. We don't have the cloud version of it in the public Drake, but we're thinking about putting it over. And there were some really subtle bugs that it would find that we actually found in simulation, and then we're like, no way that could happen on hardware. And then sure enough, we saw it happen on hardware. It was really fun to because actually when we started turning on all this, the first thing we did is we found all kinds of bugs in our physics engine. Not like easy bugs, we got F equals ma wrong, but like numerical issues when things fall to infinity and stuff like that. Really subtle things. But then really like annoying things that were bad failures, I would say. But then as we kept running it, we got to the really good failures. And we burned down all the sim to real kind of stuff. And we found very subtle bugs. And this is my favorite little example. Okay, so let me see if I can, yeah. So there was this case where the robot would pick up a mug, and we saw this in reality, pick up a mug, go to set it down, and be like, And then we would set the mug down, it'd try to pull the rack out, it would pick up the mug. Actually, no, it didn't even pull the rack out. It would just go like this. And it would set it back down, and then pick the mug up, set it back down, and it just would get in this infinite loop. And we're like, okay, that's a super low probability event, right? That's never going to happen. It happened in the real robot, and it was actually an infinite loop, effectively an infinite loop. And this is why, okay? It was the night that the guys added the sensor noise to the dish rack locator. Okay, so what they did is it was a very simple noise model. It just said the perception system for the dish rack would just, on every step, pick a random number. It would adjust the true dish rack location by some Gaussian, okay? And there was a particular location of the dish rack that found this weak threshold that somebody had put in their code, where basically with very high probability, when it started making the motion, with very high probability, that it would think the dish rack was out enough to put a mug down. But over the time it took to actually put the mug down, with very high probability, it would find at least one sample that said the dish rack was too far in, and I had to go back and set it down. So the whole planner would go, okay, fine, put it down. But then by the time it went again, with very high probability, it was out enough. And this thing would just go like this. The day we saw that in Real Robot, on the Real Robot, we were like, a simulation is great. And it was like this. This is what I mean about the crazy hard simulation. The robot was trying to do in simulation, it was trying to put dishes away while the dish rack was going like this, right? Which is nuts. But being robust to this inferred robustness in the real world. Okay, so this type of programming paradigm is very simple, but it's actually used all the time. My favorite example, actually, I used it under Actuated too. Mark Rabert used to talk about his simple controller for a hopping robot. And the best thing about it is it fits completely on one page, and it looks like this. He's got a flight phase, then a landing phase, then a compression of the spring phase, and then it pushes off with the leg, and it unloads, and it's back in the flight phase, right? He used the language of state machines to talk about his controller, and used that language to describe a fairly complicated controller on a page in his book. It's one of my favorite examples of like rich behavior coming out of a simple state machine. And it actually, for me, it's a goal that we should aspire to with our best control designs. It's something so simple could achieve something so complex. But normally, when we do optimization-based control, we don't get that simple stuff out. I don't know if you've seen this version. I know Boston Dynamics puts out awesome videos all the time. This was one from a few years ago. This was Spot opening doors. Andy was a student here, so maybe that's why I like it so much. But you know, Spot is really good at opening doors. I've never seen the code. You know, I know a lot of people that work there, but I have, you know, conversations informally, but I don't know anything for real. But I'm pretty sure that's a state machine, right? That's doing all the same kind of logic we're doing here, where he's like, if someone pulls my butt, you know, then probably that case wasn't specifically hand-coded, but it's surprisingly robust behavior in the real world on a real robot with, I like to call them robot whisperers, people who know how to write these state machines really well and can make really robust behaviors out. Now, our goals as researchers are probably to do less hand-designed state machines type controllers like that, but they're getting it done in industry today. And if you look in the robotics open source toolbox, you know, there are, for instance, SMOC it's actually pretty dated now. People still use it though. This is a state machine. You know, right in ROS, people have state machine toolboxes and the like. If you look at the individual skills and the dish loading task, I should run that again as I say it, there was a simple state machine there. It was actually written in a way that was kind of a mix of procedural logic and state machine logic, but it's even non-trivial every time you pick up a mug, right? You approach, you do a little bit, you see that little visual servoing? That's ICP, remember I told you about that before? It does a little ICP to you know, I thought the mug was gonna be here, I'm gonna use my hand cameras to adjust it, and then I'm gonna insert to grasp, retract, move to my pre-place, all the stuff we're doing here. And that was done at the low-level control for the dish loading demo. My favorite one actually is that programmed a really rich behavior was when it picked up plates. Okay, so this is the sim, obviously this is real. That was a pretty complicated maneuver to get this big hand with a big robot to reliably pick up plates like that. And it was coded with the same sort of a logic where it would be a kind of it was the way we had it authored in code was a kind of a mix of procedural and state machine logic, but a simple script. It's kind of what you'd expect. And this is, the art is in picking the parameters of these little transitions and the like, but the script is exactly what anybody would write down pretty much, right? So for instance, this is, I asked Siwan, who wrote this, to describe it, and he's funny. He's like, you kind of scoop the gripper into a solid grasp. You know, and these are terminated with sensor-based feedback, right? So it would kind of scoop up until it felt collision with the hand, you know, in the palm, and then it would stop that and transition to the next thing. Okay, but these state machines are real, and they allow you to program pretty complicated things. Those couple examples were all at the sort of low level. People find that state machines, this picture, a view of the world, or you know, the one for your new system, kind of works when you have, I don't know, 10 states or something like that, or simple structure. Maybe that one's relatively sequential, so you tend to go forward until you break out. But if you get more serious and you try to build a more and more complicated robot out of this, then this paradigm breaks, roughly. It breaks in a couple ways. It just becomes very complicated to author a big diagram and get all of the transitions that you'd want correct. And people found out that it was very hard to like write one state machine and take, like, you maybe have a subgraph here. You think, I'd really love to take that subgraph and use it in a slightly different application. Have like a modular sense in the state machines. And something about the state machine architecture, people decided it was very hard to do that. It's very hard to like take a piece and use it, because you have to sever all the edges coming in, and that changes the behavior of the state machine, and then you have to rewire it to all the new places, and that is so delicate that it was very hard to do that. So the different machinery that people have authored, it actually came from the computer games world. Right? This is like gamers were writing big state machines to make their Unreal, games and the like, and it just broke. And they invented a new paradigm called behavior trees, which are very state machine-like. Since it's late, I won't talk about the details here. We have a problem that will help you think through it. But it's another programming paradigm that's similar to this, but the computation is organized a little bit differently. At every time step, you run through the behavior tree, and they can tell you whether you're done and you should stop, or whether you should continue on to the next one. Each of these nodes has a little bit of programming logic. And the consensus has been that this slightly different programming paradigm allows you to write much bigger machines that are much more modular, where people will frequently take their behavior tree, a big chunk out of this behavior tree, and stick it in another behavior tree and immediately be happy with the behavior. It really does come out of like gaming. That's where it started. But roboticists use it too. In fact, to prove that, I found another a reference to the ROS behavior tree package. Yeah. Right. This is PyTrees ROS, right? And it's actually really good. It's a really nicely architected software package. And you can make a behavior tree fit in the same way we did a state machine. That could be a system that's reasoning about all the discrete logic and that fits right into the systems framework. I haven't made it easy for you to do that. And so again, at the very end, I'll ask just, or over time as you think about it, I could try to make some of these things easier to do. But okay, I'm sorry that I'm just gonna keep going a little bit since I won't do the stretch right now, but. So the interesting thing is that a lot of the state machine and even the behavior trees, they get you to a certain place, but oftentimes people need more. And the reason you tend to need more is if you have some very long-term planning required. If there are consequences of your actions now that need to be sequenced in a certain order to achieve a long-term goal. Like maybe I need to have all the mugs in the top shelf, in order to accomplish my dish loading. And that takes it to a different paradigm, which is the planning paradigm, where you tend to take these low-level skills and combine them into some sort of a skill framework. And we'll work on skills and motion planning a lot going forward, but I want to foreshadow that here with just thinking about how it's related to state machines. Okay, so for the dish loading example, there were a bunch of skills like pushing things out of the corner, picking up mugs, picking up silverware. These were all authored as different skills. And then rather than write down one time some big automaton or some big state machine, we would define the rules of interaction and use a planner to decide what the action was on every time step. Okay, and that's got a long history in AI. Strips is the original name of it, this planning architecture, where you just say, I've got an initial state, I've got a goal, and I'm basically, think of it as doing graph search on a discrete graph, saying I'm going to do this action, and then this action, and then this action in order to accomplish a long-term goal. You have an initial state, a goal state, and a set of actions where those actions are authored as I have a potential edge saying based on what conditions must be satisfied for me to do a pick X, and then what conditions will be satisfied if I do pick X for a while. And strips is the old version, padiddle, the planning domain definition language, is the newer, richer language of these things. I could tell, I'll just move past the details of that, but I think it's super interesting to look at how this worked in the specific application of the dish loading, okay? So we had our skill concept, our action primitive, which basically you had to, in order to write an action primitive in the framework, you had to basically say, given the current state, could I run my skill right now, yes or no? And if I were to run that skill, what would be the new state? And that's pretty much it, you know? And the skills that we did, the actions that we implemented were, this is the entire list. Open dishwasher door, close dishwasher door, start dishwasher. That was pretty funny. It wasn't actually plugged in because we weren't allowed to run water to the lab in that particular way, which is probably a good idea in retrospect. That would have, but the robot, we built a whole skill with a capacitive sensor because it was a smart dishwasher, right? So you needed to put like one of your stylus from your a standard stylus to make a capacitive sensor work. And we mounted it on the back of the EWA, and we had a skill that would just go and boop, and the dishwasher would go doo-doo-doo-dee, and we were good. Yes?
What's the optimistic mode? Optimistic mode?
Yeah, right. Is there a pessimistic one too?
Just put mode is about it.
Yeah. So my guess is, I actually don't know. I would go look. But it's possible to get unjammed by these kind of things. They would be, there was an aggressive version that was more optimistic. That's pretty funny. I copied the list, but I didn't actually look at that one carefully. Yes?
So there's no learning so far, right? It's only planning.
Yeah, that's a great point. There's no learning so far. And I think that's, my last slides are like, how do you put learning into this? But this is not learning so far.
Second question, how do we evaluate the goal? Because for example, if you have a dishwasher and you want to put a log into like the sticky thing in the dishwasher.
Yep.
And for some reason it kind of drops out after you put it. So you have actually the goal achieved, but it falls out. But then like restores the whole space, so you kind of put other mugs there.
It's a hard problem. So yes, in the limitations of this, one of the big limitations is that you need to define a state, a symbolic state of the world, and I'll put this on a slide in a minute, and you need to somehow have the perception system tell you what the state is, and have a model for how that state's going to evolve. And that is a really hard thing to do, and it's a limitation of the framework. So goals are typically authored in a logical way, but they are often impoverished because of all the things that can happen in the world. The dishwasher state was things like, are the clean items put away? The number of clean items put away, the number of dirty items available. It's a very discrete state that summarizes what the robot perceived in the sink. And that's all right out of the code. Okay? But if you take those discrete logic and author yourself a bunch of skills, then you can do a little planning on the fly and get all the robustness that you see. So this was like the example of someone went and closed the dishwasher rack and it had to set the mug down. That's exactly what it was. The robustness here made us susceptible to the crazy noisy racks, right? So Boston Dynamics, they like kick the robot, right? But we just closed the dishwasher. We could have kicked the dishwasher, I guess. Okay, but this time, instead of a state machine making that robustness, it's a planner that makes that robustness. You just say these are the actions I can do. This is when I'm allowed to do it, and what the outcomes are going to be, and I roughly do a graph search, a richer version of graph search to make that happen. And you can get the same levels of robustness out. This is exactly what you were asking. The problem with this approach, the limitation of this approach, is that it requires somehow to take those discrete states and acquire them from perception, okay? And you have to have a model of how that state is going to evolve if I apply certain actions. And these can be very brittle in the real world. So there's been famous debates about this, and one of the most famous maybe was Rod Brooks, who wrote a nice paper called Elephants Don't Play Chess, arguing against intelligence without reason. There was a line of arguments that he made basically saying the AI community is going down the wrong direction by trying to summarize the world with symbolic states. It's just too hard. Elephants don't play chess. They don't do planning like this on every time step. That's the chess analogy, okay? And when he was saying this, it was right before he went off and started iRobot and made Roomba, which was highly successful without playing chess, with just kind of bumping around. And you know how it did that? The Roomba application, initially at least, it's probably evolved now, but it was Rod's version of it was called the subsumption architecture, but it was the precursor to behavior trees. Roomba was much more like a behavior tree, and it was a saying don't rely on planners, it's too brittle for the real world. Symbols whose grounding is in physical reality has rarely been achieved, says Rod. And then I'll just end saying that I do think one of the new challenges, and you'll see lots of papers about this right now, is how do I make skills, this sort of skills framework, long-term decision-making, work when those skills are learned, right? Where now, the way we're picking up plates at TRI now is with, policies, controllers that were acquired by learning, right? And we have demonstrations that are much more robust to perception failures and other things like this now. They can pick up plates very robustly coming out of machine learning. And the question is, if I want to put that into a skills type framework, so a high level task planner can reason about it or write a state machine around it or whatever, how do you combine the new tools from learning with the classic tools from planning? And that's a big topic we'll talk more about. Good. The last thing I'll say is that we're making because you have your project proposal next week, the PSAT will be a little smaller this time to accommodate. But please, again, ask us about project proposals and use the pre-proposal as a chance to get good feedback. Okay, thanks.